So I want to end this video by giving you a few thoughts about arc length as a parameter and a little bit of perspective as to why we care. So the last problem, if anything, should convince you that reparameterizing a curve to use arc length is sort of, I'm actually going to say, at best, annoying. At worst, I'm going to put impossible in quotes. And why is that? Well, the one thing is that a couple of those steps in that process, so one, the whole computing this guy here, so one of the steps is we have to write s as a function of t, and that involves us computing this integral. Well, this magnitude sort of hides within it a square root. So all of these integrals generally involve us having to deal with integrating a square root, which can be at best annoying. Think of the last example we did, or think what's one of the other goodies with square roots. We might have to do a trig substitution to evaluate that integral. So those are annoying. But there are other integrals that involve square roots that we can't really write down an explicit formula for the antiderivatives. So this is one of those things that it could be very annoying or impossible. Well, even if we can do that, we have to then solve for t in terms of s. Could also be really, really difficult, if not impossible. For instance, what happens if we would get an expression like s is equal to t to the fifth plus 3t plus 7? How do you solve that for t? Now, if that's quadratic, maybe you could use the quadratic formula. There's actually a formula for cubics and one for quartics, powers of t cubed and t to the fourth, but there is no general way to solve a fifth degree or higher equation. That's something you'll explore maybe in a later math class if you take one, but it was actually the subject of intellectual curiosity for hundreds of years until someone actually proved that you can't do it in general. So at best, this step is difficult, if not impossible. So what does that mean? Well, that means trying to describe arc length or a curve using arc length as a parameter is pretty annoying, if not just impossible to do. So you should then legitimately ask, well, why on earth would we want to do this? What do we actually get out of using arc length as a parameter? And we talked about using arc length as a parameter is nice because it gives us a uniform way to trace out a curve, but I'm going to do a little bit better than that in the next video. So one of the good applications of why do we care to use arc length as a parameter is this idea of curvature. So the sort of more formal idea is measuring how the unit tangent vector changes. I'll draw a picture and sort of tell you what that means or how I think about it. So we have some sort of curve here. And what we're really asking is essentially how curvy is this curve? And, how do we think about that? Well, we generally say that we'll agree that a line is not curvy at all. It has curvature 0. And we want to then say, well, how does the curve deviate from a straight line? And one great way of doing that is to look at if I draw the tangent line at a point and the tangent line at a point nearby, how different are they? So we can measure how the tangent lines are changing. We're talking really here about curves described via vector-valued functions. So instead of talking about tangent lines, we want to talk about how are the tangent vectors changing. But we saw in a previous slide that a vector has two ways to change. Its magnitude can change, and its direction can change. And we only here care about how is the direction changing, and so we get that by considering the unit tangent vector. So if I draw the unit tangent vector to this curve at a point here, and a point here. So we'll say this first point is at some value t0. This second one will be the unit tangent vector at some different time. So what we want to say is how is the unit tangent vector changing. So we can construct the usual difference quotient by saying, well, we'll look at how that's changing over, well, how far we've gone here. And what's a great way to talk about this, this distance that we've traveled? So this distance is really easy. It's easy to write if we use arc length as our parameter. And so then we can measure this, this change very, very nicely. So what we can write, so what measures how something changes in calculus? Derivatives. So we can set this up formally, and when we do a more formal study of curvature, we would do that. This is just to give you an idea as to why we care. But we can set up that this thing here, the curvature will be our measure of curvature. So that's a vector. Actually, the curvature will be the magnitude of that particular vector. Now we use this, this Greek letter kappa to indicate the curvature. So the nice thing is that this definition should make sense in terms of the arc length parameter. But what we saw via that one example is that the arc length, well, it's really difficult to describe a curve using arc length, much less calculate a unit tangent vector, then take its derivative. So what do we ideally want to do? Well, we ideally want to work with the parameter that we started with. And this is actually a very common theme that you're going to see in multivariable calculus. Arc length is a very useful parameter to make definitions, but at the end of the day, you actually want to work with whatever parameter that you start with. And so just to sort of show you how to do that here, let's talk about this. So we know here that instead of doing this, I'd rather compute the unit tangent vector in terms of the original parameter t. So we can actually write this using the chain rule here. We'll think of that now as a function of t. We would then want to differentiate it with respect to t, and we're allowed to do that provided that, well, that we use the chain rule. So we can write this down, and this is a little bit nicer, at least this first term is nicer to compute because we can compute it from the original parameterization. We also then can go ahead and rewrite this. We know that ds dt is the multiplicative inverse of dt ds. I can write that like this, right? And now there's actually a nice way to compute ds dt, because remember that we have a formula that relates the arc length and the original time parameter. And that is precisely this thing that I'm writing down now. So how do we find ds dt? Well, it's just fundamental theorem of calculus, right? So the fundamental theorem of calculus tells me that ds dt is just r prime of t. And so now this lets us rewrite that, that curvature formula in terms of the parameter t, which I'll indicate very explicitly by writing that. So we want to write this down now in terms of t, and that's not particularly bad. It's just this divided by r prime of t. Everything here can be computed exactly in terms of our original parameter t. So there's no arc length parameterization necessary. So this is a common theme in multivariable calculus. You're going to need to formulate definitions using the arc length parameter, but you don't want to work with the arc length parameter. So you then try to get around that. And one way that you do that is you always have a relationship between your arc length parameter and your time parameter, which is just this formula. And the chain rule allows us to then re-express everything in this original definition here in terms of our original parameter. So this is a common theme. You're going to see this again. but this is one good example of why we care about using arc length as a parameter. Okay, so another application of this is work along a curve. So to illustrate this, I'm going to grab this, this unused tripod right here. I guess you guys can't see the floor, but when we were talking about work before, we just moved things sort of in a straight line path. Well, there's no reason to necessarily do this. I can now sort of just move all over the place and end up at the same point. So the thing is, now that I'm dragging this along a carpet, there's friction. So I have to fight friction at every single point along this path. And that could definitely depend or affect how much work we do moving this from one point to another. It might very much depend now on how we move from that point to another. So a question that, that we can try to ask now is, well, how do we do this? And so this is actually something that you're going to explore a lot later on when you study integral calculus of vector fields, but I want to at least give you a preview of that now. So what we have here is we have a curve in the xy plane, or in the xyz plane. We're just going to go in the xy plane just for sake of illustration. And what we want to do is we have a force, F, that's actually going to be defined at every point in the xy plane. So it takes a value here, it takes a value here, it takes a value no matter where we are. And so this force could be friction, it could be something else, it doesn't really matter. But what we need to do is we want to say, okay, well, how on earth do we figure out that amount of work that we do? So we do the same thing that we normally do, which is we first slice this, this curve up into different segments. We'll use those points exactly there. And then we want to approximate here. So what do we know about work? Well, if those little curvy segments are actually lines, we know that the work will actually just be the amount of force in the direction of motion. So how do we say that here? Well, so the first thing we want to do is say that each slice is a line segment. So this work is going to be force, the amount of force in the direction of motion. Now, how do we say that? Well, we need to figure out, so if we have our force right here and it's a vector that's pointing there, I need to know how much of it is along the curve, which means how much of that is actually parallel to that tangent line. So we definitely do know how to find that, well, a vector in that particular direction. It's just the derivative of the vector-valued function that we use to describe that. But in order to find the distance, or the length of this little segment, what is a natural parameter to use? How about one that measures the distance? So we want to use our arc length parameter here. And we know that that'll just be some little change in the arc length parameter. So what I need to do is I need to take the projection, and really here we don't want the orthogonal projection, we want the scalar projection, right, of this force onto the tangent vector, which we can just do by that, times the actual displacement here. So one thing that you hopefully showed at some point was that if we consider the unit tangent vector, well, as a matter of fact, I'll show you now. So this scalar projection, what is it? It's going to be this force dotted with r prime of s. And we have to divide that now by the magnitude of r prime of s. And we actually have a pretty useful way of, if I just look at this, what is that? Well, that circled expression is exactly the unit tangent vector as a function of s. So this thing here, f, we can describe our x in terms of s. We can describe our y in terms of s. And as we just talked about, that r prime over its magnitude is the unit tangent vector. And so along one of those little segments, that will be the amount of work we have to do. Now, as before, how do we add all of those together? Well, we integrate. And what I'm about to write down now is an example of a line integral, which is an object you're not really going to discuss for a while. But the idea is that we need to add up all of these little work segments along the curve. And we're going to say that, well, in order to do that, we need to shrink this little change in our arc length parameter to 0. And we need to add up all of them. And the definite integral does that. What this integral over c means is we're just adding up all of these segments along the curve. So that's sort of the conceptual process that you're doing. This is an object that you are going to study later on in the when you study integral calculus of vector fields, but it's something that sort of tells us right now that it's important to use arc length as a parameter. And by the time you get to this, it's probably going to have been a little while since you discuss arc length as a parameter. So it's not bad to sort of preview something that you're going to study much more in depth later. Once again, we do not want to look at using arc length as a parameter. We don't want to write the unit tangent vector in terms of s. We don't want to write our force F in terms of s. We want to use the original parameter, t, and we can do a similar argument as before to actually do that, and you will do that later on when you actually study this object in more depth. But this is another example of why we really want to use arc length as a parameter.